Yeah, we're a small group today. Anyway, my name is Janice Griffin. My presentation is on my top 5 PostgreSQL querying tuning tips. So just a little bit about myself. I've been a long time DBA. Started out with Oracle version 3 back in the day. Actually, I was still going to college, and I was working part-time at a manufacturing firm, and they bought Oracle. One of 2 companies in Colorado. And nobody wanted to be the DBA, so I raised my hand. But anyway, worked with many different database types throughout the years. Postgres has been an interesting one for me, so I thought I'd use my top 5 tips of what I've used on all the others to see how it performed. It was kind of interesting, so I thought I made a presentation out of it. We're going to talk about my top 5 tips. They're listed right there, and I've only got 20 minutes, so I'm going to get going. First off, tuning is hard, and a lot of times it's just trying to figure out who should tune, which SQLs to tune, and I think it requires expertise. You need to know how to read an explain plan. You need to know the different data access paths, the different join methods, which ones are the best to use for your particular SQL statement. And I also think it's wise to know what the business is using that SQL for. Years ago, I worked for a manufacturing firm, which actually was, one that had Oracle, and we were running these horrific reports every month end and slowing everybody down. And so I went to the accounting clerk that was running them. I said, "What are you doing with them? Who's using them?" And she said, "I don't know. I just put them in a filing cabinet." Nobody was using them. That was the quickest tuning I could ever did, is just shut down those reports. But so it's smart to know the business aspect of it. And then it just takes time. There's no cookie cutter approach for each SQL statement. You gotta kind of look at it, figure it out. But and it can be never ending, but it's a good thing if you get good at it. So my tip number 1 is monitor wait time at the statement level in the database. So if you don't have a monitoring tool, don't care what type of tool it is, just make sure you're not only monitoring total time. You want to monitor a SQL statement as it processes through the database, recording off the resource it's either using up or waiting on, and getting key metrics that you can actually quickly see. I know this is a really tiny print. I can zoom in here a little bit and kind of show you, but as you can see here, I'm seeing my top 10 SQL statements. The first 2, basically are taking all the time. All the other ones are hardly taking any time in the database. And then you can get some, great ideas of how many calls it's making, what is its average wait time, what's its response time, how many where it's waiting, whether it's I/O, whether it's CPU, whether it's using a lot of memory. Next tip is to review the explain plan. Now, Postgres just gives you an explain, which is an estimated, cost of what that query is going to cost. Now, the number is arbitrary. So if we look at this explain, and you can do this at the command line, there are different tools, and I think I have some examples that give you a graphical plan. But you just do explain, and then you give it a query. And I'm using this DVD rental database, and it's a simple query that I'm getting here. But you can see it says, it's saying it's going to do a seek scan, which means a full table scan on film. Then it gives you a cost with a ... and another cost. Now that is not seconds, milliseconds or anything. That's just an arbitrary cost of I/O and CPU. And it's in the, so 76.50 is really the runtime, and the before the ... which is 0 right now, is basically the startup cost. But it's just an arbitrary number. It does get bigger as the more the query is more expensive. But you can't say it's time, so don't think that it has anything to do with time. And again, it's just an estimate. Now you can do explain analyze. Now explain analyze basically will go out and run the query. So be careful with explain analyze in production, especially if you're doing inserts, updates, any time of data manipulation, because you'll want to roll back that explain because it actually will change the data. So, just be careful when you're using it. But I like explain analyze because what it will do is it'll actually give you more information. It'll give you the actual time in milliseconds. So not only does it give you the arbitrary cost, it actually comes up and says, okay, planning time took for this one step 0.064 milliseconds, and oh, by the way, the actual time to run it was 0.421 milliseconds. So, and it actually brought back one row. What I like about this is you just can't look at the rows that it has at the steps. With Analyze, it'll tell you how many rows it touched and threw out. So it did a seek scan, so it read, the table had 1,000 records, it read all 1,000. It only needed one row and threw out 999. So the total planning time and execution time, took about half a second, or 500 milliseconds if you round up. Okay. So let's see, what else was I going to say? Just to be careful with production, I guess, is all. When you look at the explain plan, what I look for is expensive operators. And I do look at the cost and look at the row counts. Not just the row counts for each step, but what the rows that it touched and threw out. Because that's going to give you a clue of whether it needs an index, or it's going to give you some ideas of how to tune it. I also, focus on SQL scans, seek scans, primarily because they're full table scans or index scans. Not that those are bad if your query warrants it, but if you're returning one row as a result set and you're reading millions in the explain plan, then you've got an inefficient query, and there's a better way to rewrite that to actually get it to work. So also look at the filtering conditions. And this is really important to know which step the filtering is happening, because you want to filter in the earlier steps in the explain plan, as well as instead of reading all the data and then at the end filtering it out, because you're just throwing away data, so you're reading too much. Oops, didn't mean to do that. Also, review the join methods. Nested loops are usually efficient for smaller data sets, mainly one large table and a bunch of lookup tables. So if you have a detail table that holds all the details, and then you have to look up to get the actual values, and the lookup tables, they're relatively small. Anytime you have that condition, you should be doing nested loops. Never hash joins. If you've got that condition and it's doing hash joins on your look, you're probably missing an index somewhere. And so it's the query planner is thinking, oh, this is too expensive, I'm going to hash it. So just remember and know your data, that if you've got a lookup table, several lookup tables and a detail table, you should be having nested loops. And I'll show you that in my case studies. Hash joins are good for very, very large tables, usually analytical data warehouse type queries, where you've got millions of rows in one table, joining it with million rows in another table. Same with merge joins. Merge joins are efficient for large data sets. Just beware that merge joins have to sort the data, so it's a little step, which sometimes is more efficient than a hash join, but mostly hash joins win over. Okay, look for common mistakes in an explain plan. Functions around index columns. Postgres can't use it. Can't use the index then. So if you put a function around that index column. You can create a function index. Postgres has function indexes. So for example, my example shows here that I'm creating, I'm creating index lower title IDX. And because I have this in my, in the code, I make that part of the index, so it can use that index to do it. So that's a function index. Beware of nested views. Nested views, like a view upon views, where it's going out and probably doing something else that you probably don't need in your query. That's just bringing back too much data, thrashing memory, and increasing I/O, and also eating up CPU while it's doing it. So, that's the trifecta of using nested views. Avoid that if at all possible. Using cursor or row-by-row processing, doing fetches and doing row-by-row. Postgres is a relational database. All relational databases like set processing. Work in sets, not row-by-row. We kind of think row-by-row, and I think that's where it gets into the coding, but relational databases don't like that. Missing and poor indexing, look at that, beware of that. And also look for problems outside of the plan. It may not always be the execution plan or the explain plan. It might be missing or stale statistics, or if you haven't vacuumed in a while, so you've got a lot of dead tuples out there. Data misconfiguration, if you haven't configured your memory right. No database constraints. And I've got an example of that in one of my case studies. Because if you set up the right relationships within the tables and put constraints on them, foreign keys and primary keys, that gives the query planner more information and it can do the right thing and create a good explain plan. Okay, so tip number 3 is gather then all the object information that's in the query. Go out and know what your query is doing by looking at the table definitions, know the sizes of the tables. If it's a view, figure out the underlying definition of that and figure out maybe you cannot have to use that view. Know the rows, know if it's a partition table. All that gives you more information that you can somehow tell the query planner and it'll help it make a better or do the right thing and give you a faster query. Examine the columns, especially in the where clause. Look for the cardinality of the column. Is there data skew? One thing neat about Postgres that I like is it doesn't cache the plan. Question?
Yeah, quick question. What is data skew? What do you mean by that?
It means you have a column which has popular values and unpopular values. So, for example, one of my case studies, it's a history table. And so it's on a university, and they never deleted out of it. They canceled. If a student dropped or canceled, they just marked the cancel flag Y, and otherwise it'd be in, no, it's an active record. Well, the data skew in that is, very few Ys, and all the rest were active. So, that would be data skew. One thing about that in most other databases is, like Oracle, SQL Server, they cache the plans. And they like to sniff the bind variables or the parameters that are coming in. Well, Postgres doesn't cache any plans. It creates the plan every time it executes it. Okay? So you don't have to worry about it. So if say you've got 2 values in a column and you've got, millions of one value is 1, and the other value is, let's say, 5, and you only got 5 records. One would use an index quite nicely. The other one would be a better full table scan. What you can do with Postgres is you can create a partial index. And it's smart enough to know, I put 5 in there, it'll use the index. It won't cache and sniff that parameter and cache the plan and do the wrong thing. And that's been a problem with both like SQL Server and Oracle for years to try to tell the optimizer not to do that, Okay, other indexes, look for, the indexes on, always look at your join columns. They should always have an index. Filtering columns, if they're, big tables, they should have an index. So be sure to look for indexing. And then, it's easy enough to create an ERD these days, an entity relationship diagram, to see how tables are connected. And I think this helps you understand, the constraints, definitions, and the indexes, so you can quickly, especially if you've got a table of, a query that has 10, 8, 11, 12 tables in it. It's nice to make sure you've got all the joins correct, all the columns there. And then also know when your automatic vacuum or analyze are happening, because that'll have a yo-yo effect on, cleaning up the data, and it runs good sometimes, and maybe you don't do it enough, and it gets stale statistics, or the table or index gets too large. So those are the 3 tips so far: monitor wait time, get the explain plan, review it, and know all the objects in the query. So I'm going to use this case study to talk about my next tip was find the driving table. And so this actually came in from a customer of ours. It was a university where they were trying to get their billing out. I've changed it somewhat, and I've talked with this query. I use it in many different databases types. And it always rings true about how it works. So really the query was pretty simple. And actually I think it was Oracle when it came in. but I've changed it and just did a prepare statement for Postgres, and it was a select first name, last name, sign up date from student, and then it was joining on registration. That was a detail table on student ID, and then it actually took registration on the class and joined into class on class ID. So, and they were passing in a literal, which again is okay for Postgres because it doesn't cache off any of the plans, so it's not holding anything. So, they didn't have to have a parameter there. I just changed it to SQL tuning, but they were actually passing in literals for each of the classes. And then they had a date range. I changed it to be yesterday just so I could, mimic it and keep going with it. So, and then, like I said, it was a historical table, so if a student dropped or canceled, they'd make the cancel flag Y. So this was active records only. And what astounded me is, when I ran it in Postgres, it was running pretty good. You can see here, it was chugging away, and usually on my test statements, I usually run 5 to 10 users, just looping through different values, different dates and all that, and having it just run out there continually. So you can see it was taking up, some time. It was taking, on average, 45 milliseconds each execution, which to me wasn't bad. I mean, when I did this with Oracle, it was taking minutes. So, Postgres has a pretty neat query planner, I think. So let's go get the execution plan. And like I said, I do analyze, explain analyze, but you can also add a lot of other parameters onto that. So I thought it might be useful to look at the shared buffers too to see what they were doing. So as you can see here, first thing I'm doing is I do explain, analyze, and get the buffers. And the first thing it does, and how you read explain plans, is you go to the most indented first. That's the first step, and then you kind of read on out. So these arrows kind of help you here. So as you can see here, the first thing it does a seek scan, full table scan on class, and it actually brings back two rows. It throws out 998, so it read the whole table. At the same time, it does a seek scan on registration. Here, it took a lot of time, as you can see, this step. It actually brought back 33,000 rows, and throughout 46 or 47,000, if you can see there. And then finally, it does a hash join between those two. To me, lights should be going off here, because this is a lookup table. I have two lookup tables and a detail table, right? It's doing a hash join. That should be it should be nested loops. Why isn't it doing it? Well, we'll stay in the car and I'll tell you. But then the final thing it does is it does a nested loops. It actually does an index scan to student using PK, student, brings back one row, and then it does nested loops in with the hash join result set. And then here you can see the actual time of 32, if you round up, 33 milliseconds of what it takes to run that. So let's go get the table and indexes and find out all about this query. Well, you can see I did a little ERD, and you see we did have primary keys and foreign keys. Registration had an index on student ID, class ID, and canceled, with a lookup into class on class ID and a lookup into student on student ID. So they had indexes. My makeup of the tables were 1,000 in class, 10,000 in student, about 80,000 in registration. That was my data set. I went and figured that out. Okay, and you can actually do some shorthand in getting this information with the /D will give you the whole description of the table. You can do a list on these. It's kind of nice. I like the shorthand and being able to get this information without typing it all out. I have a little cheat sheet that I just have on my, by my computer that I can quickly remember them. Okay, so this brings me to tip number 4 is find the driving table. Because remember what I said, you want to get the least amount of data first and then build on it. You don't want to read all the data and throw it away at the end. You want to find the driving table that'll get you the least amount of data. So how you do that is basically, I use SQL diagramming. It's an old book that you can go out and still buy, but it's a way of drawing relationships with your query. So I had 3 tables. I take the detail table first, and I draw this upside down tree. And what you do is you basically draw this upside down tree and put arrows or links to the lookup tables. And then you figure out your joins and about how many records you're going to have by joins. That's what these numbers are. And there's math behind that. You can go and do that. And in all actuality, I don't do this step anymore because if you just index your join columns, every optimizer or even the query planner in Postgres will do the right thing. And it'll work out the join. The filtering is where it gets you. So we had two filters on this query. One on registration where canceled equals in and sign up equals yesterday, if you will. And then we had another filter on class where the name equals SQL tuning. And you can see here, 5% of the data for registration was going to come back. There was a lot of data going to come back there, right? Only 2 records were going to come back from the class for SQL tuning, probably different levels of tuning. So 0.2% of that table is going to be read. So which table do we want to drive this query by? Class, right? Least amount of data so we can build on it. So how do we do that? Well, let's put an index on class. So I built an index on class name, and ran the query again. So what you can see here is basically, the first thing it does, it uses a bitmap index scan on class name. Great, 2 rows back, didn't throw in anything else. Then it does a bitmap heap scan into class, getting the rest of the information. Then it hashes that result set, and at the same time it does a seek scan into registration. Seek scan and registration, that was my expensive step. Why is it still doing that? And in fact, everything else is the same. In fact, it's actually worse. Well, I don't know. It took 31 seconds. Well, if you add it up, it's 30. Yeah, it's actually quite a bit of time there that it took. So it didn't really improve it. So why does it do a seek scan on registration? Well, we had an index on registration, but it was on student ID, class ID, and canceled. It couldn't see class ID, so it couldn't use it. Couldn't use the index because it wasn't the left leading column. Now, I guess we could have changed the left leading column, but there were other things dependent on student ID that needed that index too. So so we really need to give more information to the query planner so it'll drive by class. So I created an actually alternate index on registration for class ID. Now we get some pretty stuff. Now our query is looking more like I want it to. The first thing it does is it goes down into reg alt. It uses an index on that, and it actually returns 76 rows instead of the 33,000. And it does a heap scan to get the rest of the information. And then it does a bitmap index on class name at the same time and gets that information. And then look at my nested loops. It's using nested loops, which is what I want it to do. I didn't want it to do a hash join because it was detailed in a lookup table with lookup tables. And then finally, it actually goes down and actually does nested loops again on the student using the PK index. Look at my time. Instead of 33 milliseconds, I get it down, if you add the planning time in it, 4 milliseconds. So you can see here, if you add that up, and got it down quite a bit. Okay. Wait. Actually, I actually did one more, and because me being the DBA in me, couldn't leave it alone, which I could. I should have been satisfied with it. But what if you put a covering index on it? If you put a covering index on it, then it doesn't have to go back to the table. It can go directly and get everything it needs out of the index. So the covering index I did is I created the same index, but in the navigation I gave it class ID, sign up date, student ID, and sign up date. Then I included canceled because canceled could change. So that's in the leaf level of the B tree, which who cares because navigation occurs in the front of the other leaves or in the other navigation part of the index. So it won't fragment. So it's a better way to do it. And now you can see my query plan is even prettier. You know, it's doing nested loops into two index only on reg-l. It doesn't have to go back to the table. So it did an index only scan. It went and got class, and then it, dipped into student. Now we got it down to, a millisecond. So let's find the driving table. My next case study basically deals with my last tip. And this has to do with the Department of Transportation. You can go on the internet and download, till I think back to 1987, every flight in the United States. And so at the time I was flying a lot, and I thought, well, you know what? I am going to see which cities are popular, so I don't have to fly there. But I mean, of course, that didn't work. But I just thought it was kind of a neat case study. So I was going to download a big data set. It's a star schema, but you have to download these tables by month, so it's tedious. And I made it for 1 year, and then I quit. But the tables were quite large. Here, let me go forward. And I wrote this table, and basically it was to get the popular flights at which cities. And it would pass in a date range and the day that I wanted to fly, and then the originating city and the destination city. And it spit out the times and which which days were the most popular. So went and got the table information. You can see it's a star schema. I had 4 lookup tables, 1 fact table, T on time, 7 million rows. And when I ran it, and you download it with Excel spreadsheets and upload it, and I didn't add any indexes to it, which I was pretty impressed, because when I ran this one on Oracle, it took 11 seconds, or 11 minutes to run. This took 2 seconds, which, I mean, it's a little sluggish, but not much. But look at what it did. It was just very, it did a lot of nested loops, but they were all seeks, because there was no other data access that you could do. So they were all seek scans in all of it. It actually threw it into parallelism, is what it did, because it saw that it was too crazy. So it did a parallelism, and then it did some strange things when I started tuning it too. So went and tried to find the driving table. And we only had really one filter that worked very well, and that was in the originating city market with 2%. We did have a filter on time for the flight date, as well as I think there was something else on there as well. But and then there's a filter on weekdays too, but that was not a very selective filter. So we want to try to drive by city market, the originating city market. So what I did was I created 3 indexes. One on the originating city market description in the lookup table, and then one on the originating city market ID in T on time. And then I actually also created a primary key on city market in the lookup table because it needed it. This actually made it a little better. Originally it was running 2 seconds. It got this down to 321 milliseconds. I adjusted that basically again by actually giving T on time a little more of an index by adding not only the originating city market ID, but the flight date, because I was passing it in. And that actually made it a little better. We got it down to 36 milliseconds. And then I decided, let's just engineer out the stupid. That's my tip number 5. Because I loaded these up, I didn't do anything with the indexes, I didn't figure out the relationships, and I ran it. And then just started tuning it without trying not to find the relationships, which I should have done in the first place. So I backed up, put primary and foreign keys on all the tables, and then ran it. And basically, it got it down just by adding the constraints where they should have been. You can see it's doing it does still a seek scan on the city market, But the very first thing it goes into is the T on time table and reduces that row set. Actually by, just gets 810 rows out of the 7 million. That's what really, saved the time. And then, of course, with having all the referential integrity, supporting those tables, index scans on all the lookup tables, right? So it got it down to, 1 millisecond execution time, or 4 seconds total for planning and everything else. But I was pretty happy with that. So the best average time, and these are the 2 case studies I was doing, and this is another reason to monitor. The 2 case studies I had, you can see there were, I had 10 queries running out here, but the top 2, those 2 were my case studies. Look how they went off the map just by tuning them. They were running out there. They just were, they kept completing because my loops kept, they're running so efficiently. Here's the entire tuning process. Another way to, reason to monitor, because you need to brag about yourself because nobody else will. So in summary, here's my 5 tips. Monitor wait time, review the execution plan, gather object information, and engineer out the stupid. And like I said, compare your tuning results and brag about yourself because no one else will. Okay. If you want to download my slides, I do keep a running a thing of stupid things because I'm always finding stupid things. So I have I always add to this list. So as I do this presentation, this list gets longer and longer. But there's some good references in here. Wait events, if you don't know about Postgres wait events, there's some good articles on that and how to get that. So anyway, thank you. I don't know what time. I'm a little over. Yeah. Okay. You didn't come in. I thought maybe I.